Okay, so what my tablet is not wanting to display, I'm using some old equations. It's just not wanting to display those, so that's okay. Let's continue on. Number 3. So, what I've got here, we know for an engine, the efficiency of that engine is the net workout divided by the heat coming in from the high temperature source. We've shown that we can, so this is the the thermal efficiency of that engine. We've already shown that we can massage that equation into 1 minus QL over QH. Now, we can prove for a reversible cycle, we can show for a reversible cycle that the ratio of heat transfers, if everything is done reversibly, is equal to the ratio of temperatures at which those heats are being exchanged. Right, now, showing that without understanding the entropy, the second law, showing that is a bit of a challenge. However, when we get done with chapter 7, we get done talking about the second law, it'll actually be pretty easy for me to show this. But right now, the proof's it's out there. I'm sure you can find it on the internet. Without really using the second law, it's a little challenging to show this. But let's continue on. Let's assume that we accept that this is okay, that this is true. And if that's the case, then that means that the maximum efficiency for a heat engine, if this is true, right? So if it's reversible, this ratio is equal to this ratio. And if it's reversible, that means it's the maximum performing device. That means that this thermal efficiency, the ability for an engine to convert heat into work, is equal to, for a reversible, let's put another subscript there of reversible, the maximum thermal efficiency, or the reversible efficiency, is equal to 1 minus this ratio of TL over TH. We need to use temperatures in Kelvin or Rankine, an absolute scale. In the English units, we can use Rankine. Kelvin always works there. This is the maximum efficiency for any heat engine we can construct. And it's only going to be determined by the low and high temperatures of the sources with which we're exchanging heat. So if we're using something like the sun, potentially at a really high temperature, we have potential of a pretty high efficiency, right? If I can put a really large value here, I can increase the efficiency. Or if I put a really small value here, I can increase the potential efficiency. Now this is the maximum efficiency. Every device we construct is going to be less efficient. It's not going to reach this maximum value. But this does set the limit as to how good an engine can actually be. The efficiency of an engine is always, this is the thermal efficiency, how good is it at converting heat into work. That's always what this quantity represents. But here we're saying this is the maximum. Right? And so it's still equal to, right, I can still put net work out divided by QH. I can still put that over here. And this efficiency is still equal to this for, I don't know if that's any better. This efficiency is still equal to this ratio. But what we're saying is we can find it based on this information. One more thing to mention up here. I am not saying under any circumstances that QH is equal to TH. That's not what I'm saying. lose a lot of points on the exam if you try to do that. I'm saying the ratio. If it's reversible, the ratio is equal to this ratio. If you put your temperatures in kelvins or Rankins. All right. So, if the calculated efficiency, if we calculate an efficiency for a cycle, an engine or a refrigerator, let's stick with an engine. Let's say we calculate the efficiency is less than the efficiency of a Carnot or any other reversible heat engine, and that just simply tells us the process is irreversible. Possible, but irreversible. It's impossible for a process to be more efficient than the Carnot or other reversible device. Okay? So, you know what I'm saying here? I'm going to have to work on those equations and get those to... They seem to display in many places. They just don't want to display on my tablet. It's just versions of PowerPoint, I'm sure. All right, so for refrigerators, remember we talked about the coefficient of performance for a refrigerator. We said the coefficient of performance for a refrigerator, we'll pull those from our notes from last time. We said that that, of course, is QL over work in. And we said we can massage that to 1 over QH over QL minus 1. So the coefficient of performance for a refrigerator, if it's reversible, meaning it's operating at maximum performance, I can replace this QH over QL with TH over TL. This is 1 over TH over TL minus 1. So this is the maximum coefficient of performance for a refrigerator. And we could do the same thing for heat pumps. Right? This is number 4. We can do the same thing for heat pumps real quick here. So number 5 for heat pump. Coefficient of performance for a heat pump is always going to be QH over work in. We said we can massage this down to 1 over, I could probably do it, but let's just not try to do it off memory here. It's 1 minus QL over QH. We're saying that the maximum coefficient of performance for a heat pump is where the heat pump is operating a reversible cycle, and that would be 1 over 1 minus TL over TH.